Welcome to the Deep Dive. Today, we're going to be diving into the world of AI evaluation, specifically focusing on RH systems. You've shared some interesting research with us, particularly a paper titled RAGChecker, Factual Language Evaluation for Retrieval-Augmented Generation.
It's an important area of research as RJ systems are becoming increasingly prevalent.
From what I understand, you're interested in understanding how to assess the performance of these systems, going beyond simply checking if the answers are right or wrong and delving into the strengths and weaknesses of the different components.
That's a good way to frame it. This paper focuses on evaluating the factual accuracy and reasoning capabilities of RJ systems, which is crucial for ensuring they provide reliable information.
So let's start with the basics. For those who might not be familiar, could you give us a brief explanation of what RJ systems are?
RA stands for Retrieval-Augmented Generation, as described in Section 2.1 of the paper. These systems combine the power of large language models with the ability to access and process information from external sources.
So instead of just relying on what they've been trained on, they can pull in additional information to answer questions more comprehensively.
Yes. They can access a vast repository of knowledge, much like searching the internet or a specialized database. The paper specifically mentions Bing Search and LangChain as real-world examples of systems utilizing RAG technology.
Okay, so we have these powerful RG systems, but as you mentioned, evaluating them properly is complex. What are some of the challenges outlined in the paper?
The introduction, Section 1, highlights the limitations of traditional evaluation metrics like accuracy. RAG systems involve two key modules: a retriever and a generator. The retriever searches for relevant information, while the generator synthesizes an answer based on that information in its own knowledge. Simply measuring accuracy doesn't tell us how these models are performing individually or how they interact.
So we need a more nuanced approach to understand the retrieval and generation processes and their impact on the final output. That's where RAGChecker comes in, right?
Yeah. Correct. RAGChecker, as detailed in Section 3, is a novel evaluation framework designed to provide a more comprehensive assessment of RAG systems. Its core principle is claim-level entailment checking, which involves breaking down the AI's answers and the correct answers into individual claims and comparing them.
So it's like fact-checking each individual statement made by the AI and then comparing those statements against the retrieved information.
This comparison is illustrated in Figure 1 of the paper. It allows RAGChecker to assess not only whether the AI is providing correct information, but also how it arrived at its answers, providing valuable insights into the system's reasoning process.
The paper also mentions that RAGChecker is designed to benefit both users and developers.
Yes, as stated in Section 3. Users looking to select the best RAG system for their needs can utilize RAGChecker's overall performance metrics to compare different systems. Meanwhile, developers seeking to improve their systems can leverage RAGChecker's diagnostic metrics to pinpoint areas that need attention.
Let's talk about those metrics. What kind of information does RAGChecker actually provide?
RAGChecker produces a suite of metrics that cover different aspects of performance, which are outlined in Section 3.3. For overall assessment, it offers familiar metrics like precision, recall, and F1 score, which provide a general sense of answer quality.
And then it gets more specific with metrics for both the retriever and the generator.
Starting with the retriever, RAGChecker focuses on claim recall and context precision.
Claim recall, if I'm understanding this correctly, tells us how well the retriever is finding all the necessary information to answer the question accurately.
Yes, it measures the proportion of claims in the correct answer that are covered by the retrieved information. Context precision, on the other hand, is calculated at the chunk level. The retrieved information is typically divided into chunks of text. Context precision tells us what proportion of those chunks actually contain relevant information.
So it's not just about finding any related information, but finding chunks that have the specific facts needed to construct the correct answer.
And that's a crucial distinction. It highlights the importance of retrieving information that is both relevant and complete. Now let's move on to the generator metrics, which I think is where things get really interesting. The paper defines 6 different metrics for the generator, each designed to diagnose a specific aspect of its performance.
That sounds like a lot to unpack, but I'm eager to dive in. Let's start with the first metric mentioned: faithfulness.
Faithfulness in this context measures how much the AI sticks to the facts it has been given. Is it using the provided information responsibly, or is it introducing information that isn't supported by the retrieved context?
So it's about making sure the AI isn't going off on tangents, or as they say, hallucinating.
The next metric, noise sensitivity, explores whether the AI can differentiate between good and bad information.
Can it tell fact from fiction, so to speak?
It's even more nuanced than that. The paper distinguishes between sensitivity to relevant and irrelevant noise. Meaning, is the AI thrown off by irrelevant details within a generally relevant source?
That's fascinating. It's like seeing how easily distracted the AI is by extraneous information. Then there's the more blatant issue of hallucination. Is the AI just making things up out of thin air?
The hallucination metric aims to capture whether the AI is generating information that has nothing to do with the sources it was given.
Next up is self-knowledge. What does that mean in terms of a RAGChecker system?
Self-knowledge measures how much the AI relies on what it already knows versus actually utilizing the new information it has retrieved.
So ideally, we want the AI to be learning and incorporating the new information, not just defaulting to its pre-existing knowledge base.
We want to see evidence that the AI is truly benefiting from the retrieval process and not simply regurgitating what it already knows.
And finally, we have context utilization. Seems like a pretty straightforward one.
It measures whether the AI is actually using all the relevant information it found during retrieval, or is it just skimming the surface and not really integrating the new information into its response?
So high context utilization is a good sign. It means the AI is effectively putting that retrieved knowledge to work.
Now that we've covered all these metrics, let's see how RAGChecker performs in action. The paper describes an experiment where they tested 8 different RG systems, as outlined in section 4.1.
8 different systems. That sounds like a comprehensive test. What kind of systems were they?
They tested these systems across 10 different domains, ranging from Wikipedia to AI science to novels. Each system used a different combination of retriever and generator, which allowed them to compare the performance of different approaches.
And they used a variety of retrievers and generators, right? What were some of the specific examples mentioned in the paper?
They used retrievers like BM25, a classic approach, and E5 Mistral, a more recent dense retrieval method. For generators, they had a mix of open source and proprietary models, including GPT-4, various Llama variants, and Mixtral.
This diversity in both retrievers and generators is crucial to see how different types of models perform under RAGChecker's scrutiny.
The result of this experiment, which are summarized in Table 3, provides some very interesting insights. But I think we should give our listeners a chance to absorb all this information about RAGChecker itself before we dive into those results.
That's a good idea. Let's take a moment to let everything sink in, and we'll come back and explore the fascinating findings of this RAG evaluation experiment in Part 2 of our deep dive. Welcome back. Now let's delve into the results of the RAGChecker experiment, which are presented in Table 3 of the paper.
The researchers evaluated the performance of 8 different RGAG systems across 10 domains, as detailed in Section 4.1. Each system used a different combination of retriever and generator, allowing for a comprehensive comparison.
Did any particular system emerge as a strong performer across the board?
Yes. The system utilizing E5 Mistral as the retriever and GPT-4 as the generator consistently performed well.
That's interesting. Can we attribute this strong performance to specific qualities of E5 Mistral and GPT-4?
The diagnostic metrics provided by RAGChecker offer some insight into this. E5 Mistral, a dense retrieval method, appears to excel in its ability to retrieve highly relevant information. GPT-4, a powerful large language model, seems particularly adept at processing and utilizing the retrieved information effectively.
So it's a combination of a strong retriever feeding the right information and a capable generator making good use of that information.
The paper also highlights several key insights and trends that emerged from the RAGChecker evaluation. One of the most striking findings was the consistent impact of the retriever on overall performance.
What do you mean by that?
They compared systems using 2 different retrievers, BM25 and E5 Mistral, while keeping the generator constant. They observed significant differences in precision, recall, and F1 score across all tested domains. These findings are detailed in Section 4.2.
So the retriever's ability to find the right information significantly influenced the quality of the final answer, regardless of the generator used.
This underscores the importance of the retrieval stage in RAG systems. Even the most sophisticated generator can only perform as well as the information it receives.
It's like having a brilliant chef who can create amazing dishes, but their success is still dependent on the quality of the ingredients they have to work with.
That's a good analogy. The paper also explores the role of generator size and type in influencing performance. They found that larger generator models, such as Llama 3 7dB, consistently outperform smaller ones across various metrics.
This aligns with the general trend we're seeing in AI, where larger models often demonstrate greater capabilities.
Yes. The larger models showed improvements in several key metrics, including context utilization, noise sensitivity, and hallucination. This suggests that larger models are better at understanding and utilizing the retrieved context, as well as filtering out irrelevant or misleading information.
This emphasizes the importance of not just retrieving information, but using it effectively. The paper also mentioned a strong correlation between context utilization and overall F1 score. Could you elaborate on that?
They observed that systems with higher context utilization scores consistently achieved better F1 scores. This means that the ability to effectively use the retrieved information is crucial for overall performance.
It seems intuitive that if the AI is utilizing the retrieved information well, it should lead to better answers.
However, the research also highlights an interesting tension between claim recall and noise sensitivity. They found that improving claim recall, which involves retrieving more potentially relevant information, can sometimes lead to increased noise sensitivity.
So it's not simply about retrieving as much information as possible. It's about striking a balance between providing sufficient context and ensuring the AI can effectively filter out irrelevant or misleading information.
That's a key takeaway. The study also revealed some interesting differences between proprietary and open source models.
What did they find?
They found that GPT-4, the proprietary model, seemed better at distinguishing accurate information from noise compared to the open source models they tested.
Is that a surprising finding?
It raises questions about the reasoning capabilities of current open source generators. Even though open source models can achieve high levels of faithfulness to the provided information, they may still struggle with the more subtle task of filtering out misleading or irrelevant information within a relevant source.
So there's a difference between being faithful to the provided information and truly understanding it, being able to critically evaluate it.
That seems to be a key distinction, and this is where RAGChecker proves particularly valuable. It provides the diagnostic tools to assess these crucial reasoning abilities, which are essential for building more reliable and trustworthy RAG systems.
Now, I know we've covered a lot of ground in terms of evaluation, but the paper also dives into using RAGChecker to actually improve RAG systems. They experimented with different settings and observed how those changes impacted performance right.
Yes. They explored how adjusting various parameters, such as the number of retrieved chunks, chunk size, chunk overlap, and the prompts used for generation, can influence the different RAGChecker metrics. These experiments are detailed in section 4.4.
I'm curious to hear what they discovered. But I think we should pause here to give our listeners a chance to process all this information about how RAGChecker can be used for both evaluation and improvement. We'll pick up with these practical experiments in part 3 of our deep dive. Welcome back. In this final part, we'll explore how the researchers used RAGChecker to actually improve the performance of RAG systems. They conducted several experiments, tweaking different parameters, and I'm curious to see what they found.
They looked at several key settings, including the number and size of the chunks of information fed to the AI, the overlap between those chunks, and even the specific prompts used to guide the AI's response.
Let's start with the number and size of chunks. Intuitively, it seems like giving the AI more context should lead to better answers. Did their experiments confirm that?
The findings presented in section 4.4 of the paper show that increasing both the number, represented by K, and the size of chunks generally improved claim recall. This means the AI was able to find more than necessary information to answer the questions correctly. Specifically, they observed claim recall increasing from 61.5 to 77.6, when K was increased from 5 to 20, and from 70.3 to 77.6, when chunk size was increased from 150 to 300 tokens.
So more context does seem to help the system locate the relevant information.
However, it's not as straightforward as simply providing more context. They also found that increasing chunk number and size often came with a trade-off. Generators became more sensitive to noise as reflected in the increase in noise sensitivity from 34.0 to 35.4 with larger K, and from 34.5 to 35.4 with larger chunk sizes. This indicates that while the AI was finding more information, it was also having more trouble filtering out the irrelevant or misleading bits.
So it's about finding the sweet spot, providing enough context without overwhelming the AI with too much noise.
The paper also notes an interesting observation regarding the Llama 3 model. They found that this trade-off between claim recall and noise sensitivity wasn't as pronounced with Llama 3, which already exhibited a high degree of faithfulness to the provided context.
It seems that different AI models have varying capabilities when it comes to handling larger amounts of context.
Now let's move on to chunk overlap. You might think that having overlapping chunks would provide more context and improve performance, but the results were a bit unexpected.
What do they find?
Their findings on chunk overlap, which are detailed in Appendix F, show that while higher overlap ratios generally led to improved context precision, this didn't necessarily translate into better performance on other metrics. They experimented with overlap ratios of 0.0, zero, 0.2, and zero point 0.4.
So even though there was more overlap in the information retrieved, it didn't seem to significantly impact the AI's overall understanding or utilization of the context.
Moving on to the generator side, they also investigated the influence of prompts, which are the instructions given to the AI to guide its response.
I'm curious to learn how different prompts can impact performance. Did they find any notable differences?
In Appendix F, they describe testing an optimized prompt, which is shown in Figure 9. This prompt explicitly instructed the AI to be more faithful to the context and to carefully filter out noisy information.
So they were essentially trying to provide the AI with clearer guidance on how to use the information effectively.
This optimized prompt did lead to some interesting changes, particularly in terms of context utilization and noise sensitivity. They observed a general improvement in context utilization, indicating that the AI was making better use of the retrieved information.
That sounds like a positive result.
However, the increased context utilization often came with a corresponding increase in noise sensitivity.
So while the AI was using more of the context, it was also more susceptible to being thrown off by irrelevant details within that context.
It's a reminder that improving one aspect of performance can sometimes come at the expense of another. They also noted that these changes were more pronounced with GPT-4 than with Llama 3. GPT-4, without the optimized prompt, seemed to rely more on its internal knowledge, while Llama 3 was already demonstrating a high level of faithfulness to the context.
It seems that the choice of AI model, as well as the specific prompts used, can significantly influence how the system behaves and processes information. The paper concludes by offering some practical suggestions for anyone building RG systems. Could you share those with us?
Based on their findings, they emphasize that improving the retriever is a very effective way to improve overall performance. Investing in a better retrieval model, particularly one with a strong embedding model, can lead to significant gains in both precision and recall. These recommendations are detailed in Section 5.
They also acknowledge that developers might not always have the resources to switch to a completely new retrieval model. Do they offer any suggestions for improving retrieval within those constraints?
Yes. They suggest that moderately increasing the number and size of retrieved chunks can improve recall, which can positively impact the overall F1 score, a measure of accuracy.
But as we discussed earlier, there's a balance to strike. Too much context can actually hinder the AI's ability to filter out irrelevant information.
Now, shifting to the generator, they acknowledge the inherent difficulty in simultaneously improving context utilization, noise sensitivity, and faithfulness. They refer to this as a trilemma in Section 5.
So it's a balancing act, trying to improve one aspect without negatively impacting the others. What guidance do they offer for navigating this trilemma?
They suggest that our builders should prioritize certain aspects based on their specific goals and the capabilities of the generator they're using. The prompts used for generation play a key role in this process.
So it's about carefully crafting prompts that guide the AI toward the desired behavior while being mindful of potential trade-offs.
And this is where RAGChecker proves to be an invaluable tool. By providing those granular metrics, it allows developers to see how different prompt modifications impact specific aspects of performance. It empowers them to fine-tune their systems in a more informed and targeted way.
This has been a fascinating deep dive into the world of RAG evaluation and improvement. RAGChecker seems like an essential tool for anyone working with these systems, wouldn't you agree?
It's a valuable contribution to the field. It provides a framework for moving beyond simple accuracy metrics and gaining a deeper understanding of how these complex AI systems function.
Well, thank you for guiding us through this insightful research. I feel like I've gained a much clearer understanding of RA systems and how to evaluate and improve their performance.
It's been my pleasure.
And to our listeners, thank you for sharing this research with us. We hope this deep dive has provided you with valuable insights into the world of RG systems and the importance of thorough evaluation. Until next time, keep exploring, keep learning, and keep those questions coming.